Hi. Yeah. So this talk is about this ongoing work, which is with my student Pandinda, and so we are at physics department in IIT Hyderabad, and Tan Wen Wu from YITP Kyoto University, and Abhishek from here. And special thanks to Professor Hayakawa for supporting me in various fundings from Japan. So this talk has quantum collisional model and glassy dynamics. So I'm very new to glassy dynamics. So any questions and criticisms are very welcome. So okay, first of all, what is this quantum collisional or repeated interaction models? They are basically any discrete time quantum Markov process, and they are kind of fundamental in our understanding of how quantum measurements are performed in practice, like in experiments, like photon detection, generalized measurements, continuous measurements, and so on. They are also fundamental in understanding quantum thermodynamics, stochastic unraveling of Lindblad equations, and so on. And they can also be used, there are various proposals to use this to simulate dissipative quantum dynamics on quantum computers, like dissipative state preparation, like Gibbs state preparation. And they can be explicitly realized in cavity QED and circuit QED settings, and have been used to prepare non-trivial cavity states via measurement and feedback. And this is one very good reference, which is a review of, this is like a tutorial of all these things. Then we have glassy dynamics, which is like a slow relaxation of a system in a complex energy landscape containing a hierarchy of metastable states. And there is Arrhenius-like activated transitions between the metastable states. And this thing usually occurs in complex macroscopic disordered, it can be classical quantum biological systems. And it also occurs in some optimization problems and so on. So it seems like these two things are very, very different. But this is our main interesting result, and at least I am very surprised about this. So, which is that we see glassy dynamics in a quantum collisional model of qubit plus cavity. And why is this might be surprising is that this is a microscopic system. There's no explicit disorder. This thing can be thought of a microscopic model for photon detection, and it can be explicitly engineered in cavity QED and circuit QED platforms. So so we kind of think of it from a experimental realization kind of perspective. So this is one way of doing it. So we have some atom source, which can prepare atoms in some, let's say, some Rydberg states, which can be ground or excited. And these atoms are emitted also with slightly different velocities. And there is a high Q cavity, so that cavity has very low loss. And these atoms go through this. And then the state of the atom is measured, right? So the thing is that we alternatively send a ground and an excited state, and because of these different velocities, they interact with the cavity for different times, tau g and tau e. And the interaction Hamiltonian is of this form, which is the Jain-Cummings Hamiltonian. And here the cavity might have also nonlinearities, that is also allowed, right? But it has to be like in rotating wave approximation and so on, so that is basically number conserving. So this situation can also be realized in principle in superconducting circuits. In a standard superconducting circuit of like a transmon qubit coupled to a resonator, which may or may not have some nonlinear elements. So what you have to do is you have to change the detuning to something large so that these things are kind of decoupled. Then you reset to G, and then you again change the detuning back, and then it kind of evolves, and then you again reset to E, and then change the detuning back to some other value, and this you do. So this thing is kind of equivalent to this kind of a cavity, like qubit in a cavity. So these are, and the interesting thing is that the dynamics of photon number in the cavity is actually given by, in this case, that is what we find, is an inhomogeneous random walk like this, which shows the glassy nature. So how does this work out? So the usual way to think about this is in terms of Krauss operators. So a qubit initially in state S, and then after interaction with the cavity, it is measured and found in state S prime, is associated with this kind of a Krauss operator. Because of the excitation conserving nature of this Hamiltonian, if the qubit is initially in ground state and found in excited state, then we know that one photon has come out into the qubit, so that is photon detection. And if the qubit is in excited state and then it's detected in ground state, then we know that one excitation has gone into the cavity, so that is photon injection. And because we have one step with qubit in ground state, one step with qubit in excited state, we have basically 4 possibilities. So one of them corresponds to no photon detection and no injection, and then one of them corresponds to only photon detection and no injection, and then this is only photon injection and no detection, and then both of them. So these two change the number of cavity excitations in the cavity by 1, +1 or -1, and these two do not. And the probability that at any time one of these things happens is given by this quantity, and the state of the cavity given that one of these things happened is just this quantity. And the average dynamics is given like this. So these are all standard results. Now, interestingly, one can take a continuous limit of this, which is like tau going to 0. But if you take tau going to 0, you also have to scale the qubit cavity interaction in some way, in this particular special way, such that you can take the continuous limit and go to a Lindblad equation. This is also standard for collisional models, and you get the very standard Lindblad equation for a cavity with a loss Lindblad and a gain Lindblad, right? And these and the Krauss operators in these limits become these things, which is also the standard unraveling of this kind of a Lindblad equation. This has a unique steady state when the loss is larger than the gain, and this is the steady state occupation of the cavity and so on. So this can be thought of as photon detection from a cavity with incoherent gain. Like this is a standard against textbook quantum optics thing, and where the coupling with the detector gives the effective loss, and the incoherent gain can be thought to model spurious excitations in the cavity leading to dark counts. Now, interestingly, even in this case, if we do not take this limit, if tau is finite, we can kind of show that when there's no nonlinearity, there is no steady state for any finite tau. So how does this work out? So essentially, so this is again as I said, the photon number dynamic can be written in terms of a random walk, where we can explicitly find the expressions for this alpha, beta, delta. Now, the important thing to realize is that this can be cast as a random walk on an effective free energy landscape given by this kind of a function. And what we can show, we see numerically, and we can argue also analytically that if chi is equal to 0, Vn always have a lower minima at higher n. So the kind of the potential goes like this, and again it keeps going down. So if you start a random walk here, so of course you will get stuck here, and then you slowly go here and slowly go here. You can find the mean first versus time. This is the exact analytical result. And yeah, I mean, it shows the usual stuff with, it takes, if it reaches here, it takes no time to reach here, so that's a plateau. And then, so these vertical lines are the minima, the red lines are the minima, and the blue lines are the maxima. Now, so you get also randomness-like behavior. But if you switch on some nonlinearity, then you can get a whole, here also you can get lots of different kinds of Vn explicitly. Here also you can get a very rich kind of Vn. And so this is like this transmon like nonlinearity that I have taken here. You can see lots of minima and so on. And in this case, usually you get also a global minima, but it can be having a lot of local minima as well. So this is the Glassy-like behavior. So what is the summary of it? Glassy dynamics of photon number generically occurs in a class of qubit cavity collisional models. These models can be thought of as microscopic models of photon detection, can be explicitly realized in state-of-the-art cavity QED and circuit QED platforms. Effectively leads to random walk on a complex, effective free energy landscape. And the exact nature of the landscape can be controlled by system parameters. So this opens a pathway for like controlled analog simulation of Glassy dynamics in these platforms. And because the natural time scales are very small, so actually the activated transitions will occur in very small, like human time scale. And also if you try to do some of this simulation of Lindblad dynamics on quantum computers, you can get out of the computational subspace just because of this physics. And if in the context of photon detectors, you can have basically slow drift of the dark current just due to measurement back action. So with that, I'd like to thank the organizers for allowing me to present my work here, and thank you.
Any questions?
So what kind of independence you have in these coefficients alpha, beta, and delta? I missed that
So
point.
that is a complicated expression with some cos and like all kinds of things.
What is the source of this independence? These are not
so
like...
the source of this independence is the nonlinearity of the Jain-Cummings coupling. I mean, basically, yeah, this coupling is nonlinear, so that is the source of all the complicated
I see. And when you say glassy dynamics, exactly what, I mean, I guess I missed the point. I mean,
yeah, so
where is the slowness coming
yeah,
here?
so the slowness is coming from, you have, energy landscape with lots of minima, and this just keeps going down. So if you start here, you'll get stuck here, and then you'll slowly make an activated transition here, and so that's what is seeing. So you get a slow, and this is basically 10 to the 45. So you never actually, in principle, like you get just stuck here essentially.
But if I typically think of these systems has a unique
no,
state.
they don't have.
Oh, they don't have, because you said chi equal to zero.
Yeah,
limit.
for this case, actually, we don't have for any finite tau.
Any more questions? If not, let's thank Archak.